Hello, welcome. Let us continue with what we have been doing since last two classes. We have already demonstrated the concept of consistent method of consistent deformation for analysis of statically indeterminate truss through two examples, but those examples was relatively easier in the sense the static indeterminacy was one, whether it is external or internal, but the number of indeterminacy was 1. What will we do today is we will take a problem where the number of indeterminacy is just more than 1. And then we will see how to do this do the calculations. Okay. Now, so again today we will continue with the application of trusses, application to trusses, method of consistent deformation. Now, before we go further, let us recall the flexibility coefficient. The same slide I showed you some time back. The essence of the slide is two things. One is, suppose in this case we have two forces, force M, which is the moment acting at A, and then a force P at B, vertical force. Then deflection delta B is the vertical direction measured at B, and theta A is the rotation at A. And then we can then we saw that how does theta A and delta B, they are related to the corresponding forces, external forces, through this expression written in flexibility format. And this matrix is a flexibility matrix, and all these coefficients are flexibility coefficients. Okay. Now, theta A, in theta A, M will contribute and P will contribute, right. So, theta A is essentially the rotation due to M plus the rotation due to externally due to P. So, so theta A, the contribution from M is the coefficient associated with contribution from M is alpha A, and coefficient associated with contribution from P is alpha A B. Similarly, for delta B, the coefficient for M is alpha F B A, and coefficient for B is F B B. So, essentially alpha A A means it is the rotation at A due to the applied moment at A, and alpha A B is the rotation at A due to the applied load at B. Okay. So, alpha A B, these are the flexibility coefficient. This is one thing, and the second thing was this matrix is a symmetric matrix, and that directly comes from Maxwell-Betty's laws of reciprocal deflection. And since it is symmetric, so these two values alpha A B and F B A, they are same. So, we discussed this some time back. Okay. Now, we will be using this while while analyzing some of the problems where we have more than one redundant forces. Okay. So, let us take this problem. This is again an indeterminate truss. Okay. So, first thing is we need to find out what is the static indeterminacy. You see here number of members are 1, 2, 3, 4, 5, 6, 7. So, M is 7, and number of joints are 1, 2, 3, 4, 5. So, J is equal to 5, and R is equal to, here you have 2 reactions, 4 reactions, and then we have 1 reactions here. So, total 5 reaction. So, total number of equations are available 5 into 2 10, and number of unknowns are 7 plus 5 12. So, 12 minus 10 is equal to, so NS in this case NS is equal to 2. So, first step is determine the static indeterminacy. In this case static indeterminacy is 2, and if you look at this in both this static indeterminacy, it is an external indeterminacy, because you see these for stability of this truss, this support is unnecessary, this support is not required, this is extra, and instead of giving hinge at D, if we give a roller at D, then also it is a stable truss. So, this roller at C is additional, is additional constraint, and again one constraint at the the horizontal constraint at D is another additional constraint here. So, we will take these two as redundant forces. Okay. So, first step is Ns is equal to 2, and the second step is we need to identify what are the redundant forces. So, redundant forces we will take. See, in this case support reaction will be now this. In this case, yes, support reaction is C x, and in this case support reaction is dy and then dx, and in this case support reactions are A y and then A x, to total 5 support reactions. What we will do is we will take this one redundant and this is another redundant. Okay. So, and then the structure become if we remove these redundant forces, then we get the primary structure, which is determinate structure. Okay. So, let us do okay. So, this is the structure. First of all, let us number the members so that we can identify them very easily. So, this is member number 1, and then this is member number 2, this is member number 3, and then member number 4, member number 5, and then member number 6, and then member number 7. Okay. So, we have total 7 members, and okay. Now, great. Now, what we do next is we need to here it is N s is equal to 2, we have already seen. Okay. And the redundant forces are, we have taken C x as the redundant force and d x as the redundant force. Okay. So, let us say dx is equal to f1 and dx is equal to not f1, let us, f already we have used for something else. So, let us take dx is equal to x1 and cx is equal to x2. Okay. So, x1 is essentially the reason why we took x1 and x2, because it will help us to write the equation in a proper format. Okay. So, x is the redundant force in this case, and the first redundant force is dx and the second redundant force is cx. That's how I have given the numbering. Okay. Great. Now, or say this is 1, this is 2, this is 2. That is what we have written. So, this is 1, this is 2. Okay. Now, next step is we need to divide the structure into in such a way that into primary structures, and how many primary structures we can have here. The one is the primary structure subjected to the external load, then another is primary structure is subjected to x1, the first redundant force, and the third is primary structure subjected to second redundant force, that is dx, which is x2. Okay. So, we have 3 primary structures, and these 3 structures are, first is this, A, B, C, D. So, what are the supports? Support at A is hinge support. Okay. Support at D becomes roller support, because we have already taken dx as constraint, as redundant, and then there will be no support at C, because it was only roller support at C, and that reaction due to that roller support we have taken as redundant. So, this is the primary structure, which is now subjected to load 2p here, and then another load p here. Okay. So, this is the primary structure subjected to external load. Okay. And then these are the corresponding numbering also we can write here. Then the second part is the same structure, but now it is subjected to first redundant force. What is the first redundant force? Okay, write the name A, then B, C, D, then E here, it is E. So, first redundant force is x1, x1 is Cx. So, it is subjected to x1, but if you remember the previous example, we apply x1 is equal to 1 and unit load in this direction. Okay. So, this is the second redundant structure, and the third redundant structure will be A, B, C, D, E, and the same primary, same boundary conditions, but now it is subjected to second redundant force, and second redundant force is x 2, which is dx. So, it is subjected to force like this, and which is in this case x 2, we take x 2 is equal to 1. Okay. Okay. Now, the next step, so the total this is equal to this plus this. Okay. So, then this is our step 2. Now, the step 3 is we need to solve this the primary structure subjected to the external load, this is step 3. So, this is step 3 if you remember, and then we need to solve the structure primary structure subjected to the redundant forces. So, this is step 4, this and this. Okay. Now, again we know how to solve any statically determinate truss. So, I am not solving this again in this class. So, I have this solution. What I am going to do is I am going to write the solution in a tabular form. So, let us see, this is the tabular form. Okay. Now, if this is unit load at C and this is unit load at D. Okay. Unit load at D. Now, how many members we have? We have 7 members. So, these are the 7 members 1, 2, 4, 5, 6, 7, and the lengths are again all lengths are L except for members 6 and 7. So, all are L. Six and 7 becomes root 2 L, root 2 L. Okay. And for this problem, AI is same for all. So, for all members, A and E are same. So, flexibility again we can determine L by EI, this divided by. So, for this it is L by EI, which is L by EA, which is same for all, and for this case root 2 L by AE, and again it is same. Okay. Now, external load due to subjected to, when the structure is subjected to the external load. So, this is Ni. Okay. That is what we are using, and these values, the values are let us write it. So, N1 becomes 3 by 2 p, please verify these values 3 by 2 p, and but before that before I write the solution, just look at the structure. Can we reduce the problem slightly? Can we identify what are the zero force members? Yes, we can. You see, if you look at joint C, then joint C, the force in member BC is horizontal and force in member CD is vertical, but there are no other forces to balance force in member BC and CD. So, naturally this is a zero force member, this is a zero force member. So, member 3 is a zero force member, and then member 5 is a zero force member. Okay. So, member 3 is zero force member, and then member 5 is also zero force member. Okay. And N4 will be 2p, N5 is 0, N6 will be minus p by root 2, and N7 will be minus 3 by root 2 p. Okay. please verify these values. Okay. So, this is the solution of the primary structure subjected to external load. So, step 3 is done. Now, let us do step 4. Step 4 is solution of this and this. So, before you do that, again let us see whether we can identify the zero force members or not. You see, take joint C. Now, joint C has an horizontal load which is 1, and this horizontal load will be balanced by force in member BC. Now, force in member CD is vertical. There is no other vertical force at joint C which can balance the force in member CD. So, naturally it has to be a zero force member. Okay. Now, similarly, if you see joint E here, now the AE and ED, their forces are horizontal and they may balance each other, but there is no other force to balance member force, the vertical force in member BE. So, this has to be a zero force, this has to be a zero force member. Okay. Now, so at least we can say that these forces are zero force member. Okay. Member, so what are those? Member number 4 and then member number 5, they are zero force members. Okay. Now, once we know these are zero force member and it is a statically determinate truss, we can compute the forces in other members, and if we do that, I have the forces ready with me. This N1, this is written as Ni, small ni, and then write 1 because it is due to the redundant force 1. Okay, whose value is x1, but it is obtained, these values are obtained when the unit load is applied in the direction of x1. Okay. Now, these values are, this is half, and then this is half, this is 1, then member 4 and 5 zero force member, we have already checked, member 4, 5 zero force member, and then 6 is 1 by root 2 and 7 is minus 1 by root 2. Okay. So, these are these are member forces for this, and then find out member forces for this. Again, can we identify some of the zero force member? Look at joint C, this member and this member, they will be zero force member. For the same logic like this has to be zero force member. Now, look at joint B, this is a zero force member, this is a zero force member. So, there will be a component, the force in member AB has component in vertical direction and horizontal direction, but no other forces at B which can balance those components. So, member force in AB will be a zero force member. Okay. Okay. One thing I missed here, please, there is a member here as well. Okay. Now, so and then look at this, at this joint C, all these are zero force member. So, this has to be a zero force member. So, in this case, most of the members are zero force member, only members which are non-zero forces are this, and their values are just without any solution, just by looking at this we can say that if this is 1, this will be 1 and this will be 1. So, write these values. So, this is N, this we can write N I, this is 2 because it is due to unit load, but that unit load acting in the direction of second redundant force which is x 2. So, this value is 1, this value is 1 and all these values are 0, 0, 0, 0. Okay. Now, so we have done step 3 and step 4. Now, next is step 5. Step 5 is to apply the compatibility condition. Now, in order to apply the compatibility condition, we need to find out the deformation in those members. Now, what is compatibility condition in this case? Okay. Now, suppose now we have two joints, two redundant forces here, x1 and x2. x1 is at point C, x2 at point D. So, we need to consider the displacement at point C and displacement at point D. Okay. Horizontal displacement at point C and horizontal displacement at point D. We can see from the actual structure that horizontal displacement at C and horizontal displacement at D will be 0, right. Now, suppose D1 D1L is the horizontal displacement in the direction of redundant 1 due to the applied external load, okay. And D2L is the horizontal displacement in the direction of redundant second redundant due to the externally applied loads. So, D1L and D2L are essentially obtained from this structure. Okay. So, D1L, D2, not this, D1L, yes, D1L, D2 from this structure. Okay. So, the D1L is the horizontal displacement at C and D2L is the horizontal displacement at D due to the externally applied load. Okay. Now, then what is the you see, now when we apply a point load at C, this will cause displacement at C and this will also cause displacement at D. Similarly, when we apply this unit load at D, this will cause displacement at D, this will also cause displacement at point C. So, unit load x1 or first redundant force, first redundant will cause displacement at C and displacement at D, and second redundant also will cause displacement at D and displacement at C. Then what is the total displacement at C? Total displacement at C will, total displacement due to the redundant forces will be displacement due to this and then displacement due to this. And what will be the displacement due to this? Displacement due to this will be the force x1 into F11 and force x1 into F11. What is F11? F1 is the flexibility coefficient. Flexibility coefficient for what? Flexibility coefficient associated with displacement in 1, displacement into 1 means displacement in the direction of first redundant due to the force acting in the direction of first redundant. Okay. So, x1 F11 essentially is the displacement at C due to this load. Okay. Now, plus x2 into F12. What is F12? F12 is displacement at C due to this load or displacement at C due to this. So, displacement in the direction of first redundant due to the second redundant. Okay. So, that is why it is written at F12. Similarly, what is the displacement for the redundant force at point D or at second in the direction of second redundant? This will be x1 into F21 and plus x2 into F22. Okay. Then what would be the, so this displacement, this part is due to the redundant forces and this part is due to the primary structure subjected to the external load. So, total displacement at point C will be this plus this and total displacement at point D will be this plus this. This is very important. Now, this we can write in a matrix form as D1L, D2L plus F11, F12, F21, F22, this is x1 and x2. It's the same way we wrote in the case of a simply supported beam. Just before starting today's class, I showed you that slide. Okay. This is the same expression, similar expression. Now, again this matrix has to be symmetric matrix and therefore, F11, F12 should be equal to F21. Okay. This is important. This is important. Okay. These F11, F12, F21, F22, they are flexibility coefficients. So, this is displacement. So, this is the compatibility condition. This compatibility condition is displacement due to this part, which is this, displacement due to this part, which is this, the total displacement is this plus this, should be equal to 0. That is the compatibility condition, and that is written in a flexibility format. Okay. Now, what is left now is we need to find out what is d, what is these values, what is these values. Now, we know that d1L is equal to how to determine that. D1L is equal to summation of I is equal to 1 to 7 here, because we have 7 members, that is then Li by Ai Ei into Ni, and since it is displacement in the direction of first redundant, this will be Ni1. Okay. And similarly, D1L, similarly D12 will be summation of I is equal to 1 to 7 Li by Ai Ei and then Ni, and it will be Ni due to second redundant. Okay. So, this is just the unit load method, right. So, this is the displacement in the first redundant in the direction of first redundant, displacement in the direction of second redundant due to the externally applied load. Now, we need to find out flexibility coefficient F11. F11 will be y is equal to 1 to 7 Li by Ai Ei. It is F11 is displacement in the direction of first redundant when the force applied in the direction of first redundant. So, it will be Ni1 into Ni1 or Ni1 square. Okay. Similarly, F22 will be summation I is equal to 1 to 7 Li Ai Ei and then Ni2 square. And what is F12? That has to be equal to F21, that is equal to summation of I is equal to 1 to 7 Li Ai Ei, and it is Ni1 Ni2, means it is the displacement in the first redundant due to the force applied in the direction of second redundant. You can write this 1 to 7, you can verify this Ni2 displacement in the direction of second redundant due to the force applied in the direction of first redundant. So, this is F. So, like we can find out all these values. Okay. Now, next step is we need to substitute this, in this expression in the compatibility condition, and if we do that, I leave it to you. If we do that, this equation what we get is like this: 2.9143, this is plus 2.914112, this is x1 x2, and that is equal to 0. This is the we get, and if we this is the flexibility format. Okay. Now, we can solve it and determine what is x1 and x2, and what we get is x1 is equal to minus 0.586 and x2 is equal to minus 1.207. This is P, this is P. Now, once we know x1 and x2, then rest is very straightforward. Rest is we need to once we know x1 is the horizontal reaction at C and x2 is horizontal reaction at D. So, out of 5 reactions, 2 reactions are now known. Rest we have 3 reactions. So, with the knowledge of Cx and Dx, the structure becomes statically determinate, and we can find the reactions and the member forces, and that I leave it to you. So, please verify these results, okay, and convince yourself. So, that is again a method of consistent deformation applied to truss. Now, in this case we have seen the number of number of unknown, number of redundant forces are 2 here. But in this case, both the redundants are external redundant. Okay, redundant due to the support reactions. Okay, now next class we will take an example where we will see the structure which has both which is redundant too, but the redundant is one is external redundant and one is internal redundant, and we will see how to again the concept is same. We will see how this method, how the concept can be applied to that structure as well. Okay, see you in the next class. Thank you.